What specific problem does your proposed zero-shot conditional sampling algorithm using rectified flows aim to address, particularly in the context of image inversion and editing?
The proposed zero-shot conditional sampling algorithm using rectified flows, RFs, aims to address the critical challenges of faithfulness and editability in image inversion and editing. Specifically, it seeks to efficiently invert a given reference image by generating structured noise that can accurately reconstruct the original image while allowing for easy modifications through new prompts. Unlike existing methods that often require complex training or optimization processes, our approach utilizes a controlled forward ordinary differential equation, ODE, to derive optimal conditions for the reverse ODE, ensuring that the inversion process is both efficient and effective. The algorithm is designed to handle potentially corrupted images, enabling the recovery of clean images without additional training or complex processors. Ultimately, it enhances the realism and fidelity of generated images while maintaining the ability to perform semantic edits, thus facilitating practical applications in image synthesis and editing tasks.
Can you break down the proposed method step by step, explaining how the controlled forward ODE initializes the reverse ODE and how the optimal controller is derived from the linear quadratic regulator, LQR problem?
The proposed method begins with the controlled forward ordinary differential equation, ODE, which is initialized from a given image, y_0. This ODE generates a structured noise sample, y_1, that is typical for the target distribution, p_1. The optimal controller is derived from the linear quadratic regulator, LQR problem, which minimizes the energy cost of transforming the possibly corrupted image, y_0, into a noise sample, y_1. Specifically, the LQR problem formulates the control as minimizing a quadratic transport cost, leading to a conditional vector field, u_t, y_t, y_1, that guides the transformation. This optimal controller is then integrated into the controlled forward ODE, allowing it to interpolate between maintaining consistency with the corrupted input image and aligning with the true distribution of clean images, thus effectively initializing the reverse ODE for accurate image recovery.
Please provide a simple illustrative example demonstrating the inner workings of your algorithm, particularly how an initial reference image is transformed into structured noise and then back to a clean image.
To illustrate the workings of our algorithm, consider an initial reference image, y_0, which may be corrupted or atypical. First, we apply the controlled forward ODE, which utilizes the optimal controller derived from the linear quadratic regulator, LQR problem, to transform y_0 into structured noise, y_1, that is typical for the desired distribution, p_1. This transformation is guided by a tunable parameter, gamma, allowing us to balance consistency with the corrupted image and adherence to the clean image distribution. Next, we simulate the reverse process using the controlled reverse ODE initialized with the structured noise, y_1, and guided by the reference image, y_0. As the process progresses, the algorithm effectively reduces the reconstruction error, resulting in a clean image that closely resembles the original reference image, y_0. Demonstrating the algorithm's capability for efficient inversion and editing without requiring additional training or optimization.
What theoretical and practical benefits does your rectified flows method offer compared to traditional diffusion models, DMs, particularly in terms of faithfulness and editability of the generated images?
The rectified flows RFs method offers significant theoretical and practical advantages over traditional diffusion models, DMs, in terms of faithfulness and editability of generated images. Theoretically, RFs utilize an ordinary differential equation, ODE, for sampling, which allows for more efficient training and faster sampling compared to the stochastic differential equation, SDE, used in DMs. Practically, RF inversion demonstrates improved faithfulness, outperforming DM inversion by 4.7% on the LSUN bedroom dataset, and enhances realism by 13.8%. Additionally, RFs facilitate easier editing capabilities, as they do not require additional training, latent optimization, or complex attention processors, making them more suitable for real-world applications. Overall, RFs provide a robust framework that balances the need for accurate image reconstruction with the flexibility for fine modifications.
How did you validate or test your method? Please describe the datasets used, the experimental design, and the metrics employed to measure the performance of your algorithm.
We validated our method using 3 benchmark datasets: LSUN Bedroom, LSUN Church, and SFHQ, focusing on 2 primary tasks: stroke-to-image synthesis and image editing. The experimental design involved evaluating the performance of our zero-shot conditional sampling algorithm using rectified flows (RFs) against state-of-the-art methods, particularly in terms of faithfulness and realism. We conducted extensive qualitative assessments and large-scale human evaluations to gauge user preference metrics, ensuring a comprehensive analysis of our method's effectiveness. The results demonstrated that our RF inversion significantly improved photorealism in stroke-to-image generation by 89% compared to the state-of-the-art, while also outperforming DM inversion in faithfulness by 4.7% and realism by 13.8% on the LSUN Bedroom dataset. These metrics provided a robust framework for measuring the performance of our algorithm and its practical applicability in real-world scenarios.
What specific results did you achieve with your method on the stroke-to-image generation and image editing tasks, and how do these results compare to state-of-the-art methods?
Our method, utilizing rectified flows (RFs), achieved significant improvements in stroke-to-image generation and image editing tasks. Specifically, we demonstrated an 89% enhancement in photorealism for stroke-to-image generation compared to a state-of-the-art SOTA method, while maintaining high faithfulness to the input stroke. Additionally, RF inversion outperformed diffusion model (DM) inversion by 4.7% in faithfulness and 13.8% in realism on the LSUN Bedroom dataset. These results indicate that our approach not only enhances the quality of generated images, but also ensures that the outputs remain true to the original inputs, addressing critical challenges in generative modeling. Overall, our method provides a more efficient and effective solution for image inversion and editing, without the need for additional training or complex optimizations.